Okay, let's do a problem today about psychrometrics example problem that will help us understand how this all works. And it's going to be a general problem to start with. And hopefully from this general problem, we can start understanding how specific. I'm going to have a control volume that is just going to be a box. Okay, this is going to be an air conditioning system. Okay, we're going to bring in air. Okay, so it's going to bring in moist air. And so this is going to have some mass flow to the air and some mass flow to the water vapor. And we may be conditioning that air by making it cooler. And here in the summer, we want to make it cooler, or we want to make it warmer in the winter time. I'm not going to determine which that is. And so there may be added into here, either coming in or going out, there's going to be some Q dot, okay, in some ways. So how is this added? In cooling, what we do is we'll have a refrigeration, we'll have a series of refrigeration coils, cold coils, and air will go over those cold coils and it will get cooler. In heating, maybe we'll directly have some sort of a natural gas or electric resistance heating that air will go over and heat up, and it will come out the other end. Okay, it'll come out the other end as mass flow rate of air, which doesn't change, but we're going to have some mass flow rate of the vapor at 2. That's going to be different than the mass flow vapor at 1. Okay, because we may maybe add or subtract the amount of vapor that we have in that air. When that happens here down below, we may have water maybe going in or out. We may be putting in some water to humidify the air or taking out some water to dehumidify the air. This is our general system that we're going to be dealing with, the general system that we're dealing with. So what we want to deal with here, let me just look at a cooling process. So let's talk about air conditioning. We're talking about a cooling process. So in this situation, what we are concerned with is we are going to be taking heat out of the air. And what that's also going to require is that we're going to be removing water from it. And I'll talk about how that happens here. So this is what we're going to do. We're going to say that mass analysis is what we're going to look at first. So mass flow rate of air at 1 is going to equal the mass flow rate of air at 2, which is I'm just going to call the mass flow rate of air. I've already called it the mass flow rate of air, but I want to make sure that we understand that that doesn't change. It doesn't change at all. Now we're going to say that the mass flow rate of vapor at 1 minus the mass flow rate of water is even equal to the mass flow rate of vapor at 2. So basically here I'm looking at everything that has a chemical formula H2O, either in its vapor form or its liquid form. This is what I'm going to be dealing with here. Okay, so this is going to be our water. Okay, and I also know the following here. I know that the mass flow rate, let me write this in the right color, the mass flow rate of my vapor at 1 is equal to omega 1 times the mass flow rate of my air. Equal to the mass flow rate of my vapor all over the mass flow rate of my air. So this is just a way of saying if I put omega 1 in here, this is going to be vapor 1, air 1, and we know that air 1 and air 2 are the same thing, so we don't have to worry about that. And so 2 is equal to omega 2 times mass flow rate of my air. Okay, and if I put this into, if I use this definition and I put that into this equation above it, here's what I'm going to get. I'm going to get omega 1, let me change my color again, omega 1 mass flow rate of air minus the mass flow rate of my water is equal to omega 2 times the mass flow rate of my air. Okay, so I can rearrange this and say that omega 1 mass flow rate of air minus omega 2 mass flow rate of air is equal to the mass flow rate of my water, or the mass flow rate of my air times omega 1 minus omega 2 is equal to the mass flow rate of my water. And that makes some sense. If I say here that the mass flow rate of my water at 1, or sorry, the humidity ratio of my water at 1, and minus my humidity ratio of my water at 2, that's going to be subtracting those. There's going to be a difference in the humidity ratio, if I take that times how much air is going through that, how much dry air is going through that, I find out how much liquid water has dripped out of that system. So that makes sense. And this will be a very useful equation. I want to put things in terms of omega if I can. Now let's go look at our first law. We do our energy balance now in addition to our continuity balance, which we've already provided to you right here. Okay, so energy balance. Our energy balance, dE dt is equal to Q dot CV minus W dot CV plus the summation of my mass flow rate N times my enthalpy N, my kinetic energy N, and my potential energy N, minus the summation of my mass flow rate X ding times my enthalpy X ding plus my kinetic energy X ding plus my potential energy X ding. Okay. And we're going to assume that our air conditioner is running at steady state. We're not going to worry about that time where that air conditioner starts to, start up, or when it's starting to settle down. We're gonna look at that time where that air is blowing out into your house, that steady state portion of it. So this is going to go to 0, and we're going to say that there's going to be no work in our control volume. We're going to assume that the fans that are blowing the air are outside this control volume. Fans that are sucking or blowing this air are outside this control volume. Maybe you'd have a situation where there's a fan inside of it. The problem would tell you. Then you'd have to include this power term, okay? But not right now. Not what situation we have here. But there is going to be some heat transfer, okay? And then we're going to have here no kinetic or potential energy effects. Our air conditioner's not moving anywhere, okay? That's what we have. Now there we go. We're going to say 0 is equal to Q dot, the control volume, plus the mass flow rate of air times the enthalpy of air at 1, plus the mass flow rate of my vapor at 1 times the enthalpy of my vapor at 1, minus the mass flow rate of my liquid water times the enthalpy of my water, minus the mass flow rate of my air times the enthalpy of my air at 2, minus the mass flow rate of my vapor at 2 times the enthalpy of my vapor at 2. That is what I have to deal with there. Okay, I need to pause for a second. Okay, now this is an important equation. I'll put a star by it here. Because if we were solving by the tables, we would now have to go and look up what our enthalpy of our air is. And we had to remember that our enthalpy of our vapor is approximately equal to the enthalpy of the saturated vapor at whatever temperature we were at. All of those terms, okay? And what we would do here is we would say we would replace this mass flow rate of my water, we would replace this with minus mass flow rate of the air times omega 1 minus omega 2. And what would we get? We would get this. We would get 0 is equal to Q dot, of my control volume, plus mass flow rate of my air times enthalpy of my air at 1 plus omega 1 enthalpy of a saturated vapor at 1. We would have this minus the mass flow rate of my air times omega 1 minus omega 2. And then we'd have minus the mass flow rate of my air times HA2 plus omega 2 times HV2. Now you might be wondering, Dr. White, where'd you get this omega from? Remember, I'm taking out mass flow rate of air here. So if I take out and divided this by mass flow rate of air, this is going to give me the humidity ratio there. And really I've taken out mass flow rate of air out of everything, which is very useful, very useful. So really I'm going to have 0 is equal to Q dot control volume plus the mass flow rate of air times this whole thing, HA1 plus omega 1, HG1. And I wrote this as B, I should have wrote this as G, minus omega 1 plus omega 2, HA2 minus omega 2, HG2. Okay, still have to look at all that stuff, still have to calculate here omega by using 0.622 times the partial pressure of the water vapor all over the pressure minus the partial pressure of the water vapor. Those are all things I'd have to deal with there. So a lot of work to do here. Now, what I could also do here is I could say, well, look here, I could write HA1 minus HA2. And if I was using variable specific heats, I'd look it up in table A22. If I was using constant specific heats, I could write this as C sub P T1 minus T2. I could do that if I wanted to. But I'm going to look up these following things, the HG1, HG2. Oh, I forgot a term, didn't I? You're probably screaming at me. I forgot my enthalpy, my water vapor here. This is an enthalpy of my liquid water here. This is going to happen here. So this is all going to be times enthalpy of my water. That's a big term. Okay, make sure I just replaced with the mass flow rate of my water. I didn't replace my enthalpy up here. Term in, and I've added in here to make sure. So the point here is that I look at HG1, HG2, and HW. I look these all up in the steam tables. Okay, I'll do all of that. Okay. And if I want to find out what my volumetric flow rate here, my mass flow rate is, usually what I would do here for my mass flow rate of my air is I would take the volumetric flow rate of my air and I would divide it by specific volume. Okay, and I would find the specific volume by using PV is equal to RT. Okay, that's what I would do. That's what I would do in these situations. It's a lot of work. It requires us to go and get a bunch of different numbers, steam tables, calculations, multiple calculations here. And it's a good way to check your work. If you really want to make sure that what I'm going to show you next by using the psychrometric chart is right, you can always check by going and looking at the tables. And I will tell you that in your book, the homework problems I'm going to have to you, they might have you use the tables. I'm going to say use the psychrometric chart, and there's going to be a range of numbers that will be acceptable. And so I want you to use that chart, that psychrometric chart, but use a straight edge and be exact on your numbers so that you know that you can be in the right range that Wiley Plus is expecting. Okay, so that's important here. So what we could do is we can go back here to star. Up here at star, we can write it in a way that's useful for our psychrometric chart, which is this is what I'm going to recommend us doing. So now we're going to go back to star. And we would write it in this way. We could say 0 is equal to Q dot, the control volume, plus mass flow rate of my air. We're still going to take the mass flow rate of the air out, and we're going to get the following. HA1 plus omega 1 HV1 minus HA2 plus omega 2 times HV2. And then we're going to have plus omega, what was it, omega 1, no, so plus it was minus omega 1 minus omega 2 times HW. Okay, that's what we have, which is very similar to what we had up here. Very similar to what we had up here. We're not using our HG, meaning we're not looking things up in the steam tables. And from this, what would we do? We would say, well, this and this is mixture enthalpy. We would find that by looking at our psychrometric chart, by finding out wherever our value is, and going straight up here and reading off what our value is, and that's going to be equal to our mixture enthalpies. For our omega 1 and our omega 2, we're going to go over here and read out what our omega is, and we're going to go and put those in as omega 1 and omega 2. The only thing tables is liquid water. We're going to look up, this is going to be HF, the temperature of our saturated liquid. Okay, this is going to be from steam tables. And we can do that We can look this up in the steam tables because everything in a psychrometric chart has a reference of 0 degrees Celsius, which is the same reference datum that we have for our steam table. So we're good to go. Okay. Mass flow rate of air, again, mass flow rate of air is going to be equal to the volumetric flow rate over the specific volume. And where do we find specific volume? Well, the specific volume is on our tables. On a diagonal, we can read out what our specific volumes are. Okay, it saves us literally 20 minutes to do it this way. Okay, so I can tell you, go ahead, put things into the equation, look things up in the tables. You will get exact, correct answers, but you're also, what I would say is use a psychrometric chart, and that's what I am practice problems. I am going to encourage you to do on every time that we possibly can. Okay. We're going to end right here. We'll move on to our next segment.